Okay, Assalamualaikum warahmatullahi wabarakatuh. We're going to continue with the tutorial class whereby we're going to have these three examples. Okay, three examples taken from the final exam previous final exam questions, and we start with the three-phase control rectifier with the configuration of three-pass midpoint converter. Okay, so this is quite a straightforward question actually. Okay, if you look at these questions, we start with a three-phase converter shown in figure Q2b here is used in an aircraft. So this converter is being used in the aircraft system with RMS phase. So you are given the phase RMS voltage of 150 volt, and the frequency is now 400 hertz instead of normal frequency of 50 hertz. For the aircraft, the frequency is quite high, it's a 400 hertz, and the source inductance is 200 microhenry. Okay, so this is the even though it's a straightforward, but the informations, what are the given information, has to be correctly identified. For example, you may confuse between phase voltage, peak phase voltage, or RMS phase voltage, isn't it? But in this case, it's not a standard. I mean, if it's a standard commercial, we have 240 volt phase voltage, isn't it, for RMS, and 415 volt for line to line RMS. In this case, when it mentions something beyond the standards, which is an aircraft, it's not a standard, but an aircraft standard, so it will mention whether the voltage is phase, is it line to line. So in this case, it's given to you RMS phase voltage of 115 volt at 400 hertz, and LS equals to 200 microhenry. So your omega now, you have to be careful. Omega is now 2 pi. It's no longer 50, but it's 400. Okay, so the students usually make a mistake whereby they ignore this and still use the 50 hertz. No, it depends on the questions. Okay, so write the equations for the overlap angle. So it tests you on level 1, is it? This is, if you look further for the Bloom's taxonomy, it is actually a knowing level number 1, which is knowing, if I'm not mistaken. Okay, knowledge, knowledge, which is you have the knowledge, and then you write the equations. Okay, so you write the equations for the overlap angle U and the output voltage VDC. So here we have a control rectifier, therefore your VDC equation must have a alpha. That also applies to U, so you also need to have a alpha in the equation. Okay, so write the equations, and number 2, you just apply. So now is the third level, calculate. So when it comes to calculate, you are in the application level. So the first one is knowledge, and then comprehension. Level 2 is comprehension or understanding, and then level 3 is application, which is you need to calculate. You apply whatever you understood from the any theories, any things, so then you apply to a new situation. So for now, you need to calculate the overlap angle U, given that the VDC is 100 volt and PDC is 3000 watt. So you are given at the output side, you are given the voltage as well as the power. Okay, so from there you can estimate what is, you can calculate, determine what is the value of IDC, isn't it? P equals to VI, so we can get what is the IDC. So, and at the input side, you have this 150 volt, which is V phase. It's a V phase, 150 volt. So if you want to find the line to line, so you have to multiply by line to line equals to V phase, RMS multiplied by square root 3, And if you want to find the peak value, right, so you need to further multiply that with v phase root 3. You need to multiply by root 2, isn't it? Okay, to get you the v peak line to line, right? So let's have a look. So look at the marks given. It's only 2 marks and 4.5 marks. It's a straightforward question. So you get 2 marks, 4.5 marks. Okay. Next. So that is the solution. Your right equation. So this is the equation, cos alpha minus alpha. So treat everything in radian to be safe, right? So everything should be treated in radian mode. So your calculator should be changed to radian, and if you have alpha here, so that also need to be converted into radian. Okay, so everything should be done in radian, and finally, if you have the answer, the final answer, then you convert into a degree. And so you make use of you have to be, I mean, always when you want to end the solutions, you must provide the angle in radian and also in degree. Okay, it's not a compulsory, but just to make you for you to be disciplined and to train yourself to convert between radian and degree. Okay, so output average voltage, so just write that equation, VDC equals to the 3 V peak. So when you write in terms of V peak line to line to line, so this is equation, and cos alpha again deals in radian, minus 3 omega SID over 2 pi, and you get that equation. Okay, so this is what is given to you. Phase 115, so you have to multiply by root 3 V phase, then V line to line peak. Okay, so this is line to line peak, so you need to further multiply square root 2. F equals to 400, omega is 2 pi f, ls is 200 microhenry, and I use this I use MathCAD to solve this this problem. Okay, so first we need to determine what is the IDC, and then from there you need to calculate the alpha, is it? So you have ID as well as VDC. So then you need to determine what is alpha. So here I did some this is actually, if I can mark that, that is for the purpose of MathCAD to solve the problems. Okay, so I use the MathCAD. Okay, for MathCAD, it is always, if you want to use the find function, this is a function, I need to declare initial condition, just similar to what you did for your beta in your calculator, isn't it? You have to set the initial value of beta, where usually you put pi, isn't it? Pi closest to the answer, beta. So that happens here. I need to give an initial value for alpha. So this is not the answer, but this is actually the initial condition for MathCAD to solve the problem. So alpha y equals to 20 degree, and this is should be written in MathCAD given this is the equation, and then I just use a find function to get the answer. So I convert that straight away to degree, so I give me 37 degree. 37 degree. You can convert that into radian. Okay, show that in radian, what is the in terms of radian here, right? So or for you in to use the calculator, you need to use a cos is actually inverse cos minus 1, and the whole equation here, whole equation there, yeah, the whole 2 pi 3 V peak. So you have to reorganize this equation, rearrange the equation so that you get the alpha y, alpha. Forget about y and x here, just to differentiate by using the two equation. Okay, so If you use this equation, then you get that from your calculator. You can use this equation. I mean, you arrange that and you put into your calculator and you get the 37.5. Okay, hence you can also find the answer for degree for mu, the overlap angle, mu or u. So you just simply insert into your equation here, so you get that 9.22 degree. Okay, right. So that goes the first examples. Then let's proceed to second example, which is a full bridge. Okay, let's look at this example. Okay, for this example, consider a three-phase full wave 6 pulse. Okay, so when it tells you 6 pulse is full wave, 6 thyristors, 6 pulse thyristor control rectifier is supplying a DC load of 360 volt with a ripple free current IDC of 25 ampere flowing through the output. The supply voltage is 3-phase 415 with 50 Hz frequency. With the aid of its circuit diagram, 3-phase supply and output voltage waveforms, derive expression for the average output voltage in a function of firing angle. So when you look at the informations given to you, the first one is this load voltage. Okay, at this condition you have a load voltage of 360 volt, and then the IDC is already given to you, and then the supply voltage is 3-phase 415. So here it doesn't mention about whether it's a phase voltage or line to line voltage, isn't it? Why? Because it's a standard 50 Hz frequency. It's a standard commercial frequency, landed frequency. We have, in Malaysia we have 50 Hz frequency, and for the output it is always 415 volt line to line. So if it's a 415 volt, it is a line to line voltage. Phase voltage is 240, isn't it? For line to line voltage is 415 volt line to line, RMS 415. Okay, so that's given to you. Then for part A, with the aid, when you find this type of questions, with the aid of secondary three-phase supply, you must follow this to get the full marks. If not, you're not going to get the full marks, because each of these, with the aid of secondary three-phase, this actually tells you that this also has its own individual marks for them, right? So you have to sketch the circuit diagram, the three-phase supply and output voltage waveform, and then you just derive. Of course, if you do it, if you practice a lot, then you can easily answer these questions. Okay, next is part B, with the above mentioned specification. So with these parameters, calculate the firing angle, right, alpha required to obtain 400 volt at the output. Okay, even though it mentions to you is above mentioned specification, but at this part 1 here, the case now, the voltage is changed to suddenly change to 400 volt. We still have the constant current 525 amp, but now the output is already 400 volt. Right, so you no longer need to use that 360 volt. Okay, right, and then that's number 1. It's straightforward. You know the equation, then you just apply the equation to get the, just like the first example, to get the alpha required to obtain 400 volt. And part 2, sketch red phase input current IR with the firing angle equals to 0. What does it mean? So when you deal with a 3-phase 6-pass thyristor, I hope you remember when we did that in 3-phase full wave uncontrolled rectifier, the output current is quasi square waveform, isn't it? Quasi square waveform. So here it tells you that no worries, okay, if alpha equals to 0, that means you are actually operate that as the output current, the output voltage is similar to uncontrolled rectifier, isn't it? Alpha equals to 0. So therefore, this is alpha equals to 0, whereby at the actual angle, if you refer to that 0 axis of y-axis, so this is a 0 seconds or 0 angle, 0 degree here. So this is 30 degrees, isn't it? This is 30 degree, and then we have a 120 degree from there to there, and therefore this is 30, 150 degree, and then that will be 180 degree. This is 210, then this is 330 degree, and finally you have 360 there. Okay, so one complete cycle. So what this is similar to uncontrolled rectifier. So in the note monograph group, I think I can show you that monograph. So this is the quasi square waveform, section 6.3.2 in the note. Refer to that. So we have a constant current, which is this quasi square waveform, and it's already show you that this quasi square waveform is what you call it, it's an odd and quarter wave, isn't it? If you look properly, it's an odd and quarter wave. So therefore an equals to 0 for all numbers, but bn equals to 0 when n equals to even, but bn only exists for odd numbers. And then you do the evaluation, you evaluate up to pi over 2, isn't it? So this is 90 degree, pi over 2. So you only evaluate from that 30 degree to 90 degree for bn, and you do that, and finally you find out your output, your harmonic Cn equals to that 4 IDC over n pi. Okay? Bn, so because this is 0, so Cn is always positive value because it's a magnitude Bn of Bn, 4 IDC over n pi cos n pi over 6. So this is a quasi square waveform, the amplitude of the quasi square waveform. If I can test you, what will be the amplitude Cn for square waveform? If you can still remember, what is that? It is Cn equals to 4 IDC over n pi. So that is the amplitude of the harmonics, the harmonic contents of your square waveform, and n equals to all odd numbers for square waveform. But for the quasi square waveform, it is only exists for odd but no triplet harmonics. Okay, so if you look at the harmonic spectrum of the quasi square waveform, you only see the fundamental, there's no third harmonics, then you have 5th, 7th, 11, 13, 17, 19, and the rest. You don't see the odd numbers, you don't see that 3, 9, 15, they're all gone because of the cos. When you do the cos n pi 6 here, they become 0 at third harmonics, 9th harmonics, and the triplet harmonics is gone. So you use this to calculate for the to answer part 3 questions. Okay, calculate the amplitude of the fundamental, 5th harmonics, 7th harmonics. So you are given IDC equals 25 amp. So you just simply apply to Cn equals to 4 IDC over n pi cos n pi over 6. Okay, so n equals to 1 for the fundamental, n equals to 1, n equals to 5, and n equals to 7. So replacing that, you get the answer for part 3. And finally, based on the answers obtained in 3. So it tells you based on the answers obtained in 3, which means you need to use the components, the fundamental components, the fifth components, and the seventh components. Calculate the RMS as well as the total harmonic distortion of the input current. So you use the equation. So I can show you the solution now. So this is the derivation. This is what we did in on Monday, last Monday. So we do the derivation. Okay, so this is derivation. Of course, you have to fill in the gaps. Okay, there is a marks for the between that point to the answer. Okay, so write the equation and you have to solve this. You have to solve that to get to VDC equals to 3V peak line to line to get the full marks of 3 point here. 3 marks there. Okay, then for this, with the above mentioned specification, do that, you calculate, then you get the alpha. For in this case, the questions, the configuration, the circuit is without the source inductance, So you get the equation here. So remember, VDC is 400 volt. But since we have some confusion, in the final exam, some of the students still use the 360 degree because of the confused statements of with the above mentioned specification here, right? And that's why you can we still accept if the student use 360 degree to solve their to get the answers. Okay, right. And this is sketch red phase line current. So you need to sketch the waveform as well as labeling. Label correctly the answers. Need to label correctly the angle, not the answer. Correctly label the angle. Okay, and then use the in here. If you look at this, solution. It use again MathCAD, but you can still use B1 equals to 4 IDC. We'll give you the same answer, IDC over n pi cos n pi over 6. Okay, you can still use that cos n pi over 6 to get the answer. Right, just that. So you get C1, C5, and C7. Use the answer to the results here. Okay, whatever you found from this part 3, use that in part 4. So you get IRMS that, IRMS that, IRMS that, and then get the I line current. And then from there, you get this DHD by using this equation. Okay, 2 to the power 578. Right? So this is straightforward. Not straightforward, but compared to the first one, it's straightforward. But now you have to do the derivations, okay? And there's a few, you need to find the harmonics for this full bridge rectifier. Okay, right? So next we go through the last examples, which is on full bridge control 1, full bridge control 2. Okay, let's look at example. Okay, so this example is for the questions. It's actually for the is more complex engineering types of questions. This is known as a complex engineering questions, whereby you give us you are given a statement, and then you need to think, you need to analyze the question given to you, and then you proceed with how to solve that problems. Okay, so the first statement says that with the aid of a circuit diagram and supply voltage, explain the operation of a three-phase uncontrolled half-wave rectifier. So this is 3 diodes, diodes because it's uncontrolled, with a resistive load. So the output is resistive load, purely resistive load, when the supply voltage is at 180 degrees. So this question requires you to explain when you are at 180 degree. You only explain at that point. Okay, remember how to draw the sketch the waveform. Do the triangle, isn't it? So this is three phase half wave rectifier, so you only do the one triangle, isn't it? So just do this. Oh, sorry. Right, one triangle. Okay, connect the tips of the triangles. Okay, then you need to explain the circuits. Of course, you need to draw the circuits, uncontrolled rectifier. So you have a diode here. So label correctly, you can do D1, D2, D3 if you like. Yeah, sorry, it's a supply voltage, right? Okay, so you need to explain circuit. So at 180 degrees, so this is 0 angle. Where is 180? That will be the 180 degree. So you need to explain which diode is on during this time, the rest. Yeah? So if you look carefully, when you have 180 degrees, so very much we are at that point. So which diode is on? This is D1. This is the region of D2 and D3. So you can say that at 180 degree, the highest voltage for the diode is at the red yellow, is it yellow phase diode is experience the highest positive voltage, and therefore diode 2 will be turned on and diode 1 and diode 2 will remain off, will be turned off. So the output voltage will follow the supply voltage of the yellow voltage, is it? Okay, so that is sort of an explanation that you need to do. So in this case, you can also draw the output voltage. Okay, so you can draw the output voltage as well. Do that, then that is explanation. Okay, so so you just write whatever I just said just now, then that answers the question and you get 6 marks for that. Okay, and number 2, part B. A group of electrical students construct three-phase uncontrolled half-wave and full-wave rectifiers with a resistive load of 33 ohm. Okay, you have 33 ohm resistive load. Okay, purely resistive load. And you have two circuits. One is three-phase uncontrolled half-wave and the other one is full-wave rectifiers. Three-phase uncontrolled. So you have two configurations. One is half-wave, the other one is a full-wave rectifier. And assume both rectifiers connect to the same programmable three-phase supply concurrently, which means these two rectifier is connected to one programmable, which means you can change the output voltage, you can change the voltage supply to both three-phase and half-wave and full-wave rectifier. Okay, so it's a programmable three-phase supply concurrently. So this three-phase supply can be changed, can be varied. The voltage can be varied. So then the average output power generated by full wave. So it tells you here the average output voltage power generated by the full wave rectifier was 17.27 watt. So for full wave, it's already given to you the output power is 17.27. So that means for the full wave rectifier, you can find the V out. See it? Because you are given in terms of power there, so you can use power equals to V squared over R, isn't it? So you can find V equals to P equals to V squared over R, and therefore V equals to square root P over R. P multiplied by R, isn't it? V squared over R. So you have V squared equals to P multiplied by R. So V equals to square root P multiplied by R. So you can obtain what is the output voltage, and then determine the RMS phase voltage supply, average output voltage, three-phase uncontrolled average voltage, and the average direct currents of both rectifiers. So this is the thing is, you need to list down, and you make two separate circuits. You have to sketch two separate circuits and list down the equation involved and determine what is given to you. Okay, then you can solve it easily. Okay, and part C, a three-phase Y connected 400 volt 50 Hz voltage source supplies a three-phase control half-wave rectifier. So now the question turned to control rectifier. It is a half-wave rectifier with a highly inductive load. That means we are analyzing the circuit with a constant current at the output. Okay, so we have a constant current at the output without considering the effect of source inductance. So what tells you is that without the source inductance, okay, the rectifier's average output is for 880% of the maximum average output voltage. So when you apply some amount of alpha, when there is a value of alpha there, the voltage is 80% of the maximum average. So you can calculate what is the maximum average output voltage. So how to get the maximum average voltage? This is the condition whereby alpha equals to 0, isn't it? Because when you have alpha equals to 0, you have a 6 pulse output voltage. A nice 6 pulse output voltage. So this is the maximum average voltage that you can get. As the alpha is increased, then you can see there is a number. If I can change that to blue, so your waveform now is no longer okay. That's it. Okay. So if you have some value of alpha, then the average is reduced. It will be reduced, and the question tells you that it is 80% of the maximum. So you can find what is the alpha during that time to get the 80%. However, the rectifier average output voltage drops when considering the source inductance. So it's further dropped to because of the source inductance. Now you have the source inductance in the circuit. Calculate the new average output voltage and the average voltage drop if the commutation angle is 9.6. So you are given what is U, the overlap angle, and then you need to calculate what is the average output voltage, the new average output voltage, and the average voltage drop, as well as the voltage drop if the commutation angle is 90.6%. So solution is already given to you. So this is question number 2, part A. So draw that, get this VDC, then find a V line to line peak. Okay, right, so look carefully, calculate the average rate. So everything is already in there. Okay, question, and then the education again. Okay, some corrections there to the solution, no worries, and you get that answers. Okay, right, so I hope you go back and look again, try to understand the solution, and that's it. Okay, so we complete with all the three-phase control rectifier, three-phase rectifier, all the rectifier. So 8 weeks they were given to the rectifier, only for rectifier. So the rest next week we're going to start with the DC converter and the rest of the topic in power electronic EPO510. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Very good afternoon.